Go ahead and start. Why don't we start?
No, I think we'll just start. Yes. Okay. So I'm very pleased indeed to have as our next speaker Peter Koellner from Harvard, and he's going to talk on minimal models and beta-categoricity. Peter.
Great. Thanks for having me. It's good to be here and to be thinking about this topic. I've been kind of distracted by the pandemic, so it's nice to be distracted from that by thinking about this. So I'm going to talk about minimal models and beta-categoricity. There's two guiding questions. So what I'm going to do is I'm going to go back and forth between the slides and explanation. So the slides are really quite minimal. So the two guiding questions that I've been thinking about, and these are vaguely formulated. That's why they're guiding questions. The first one is about the constructible universe. So to what extent is V equals L uniquely beta categorical? And the second question concerns forcing. It's to what extent is the method of forcing a universal method for constructing outer models? And it turns out that the answer to each of these questions is sensitive to the character of the countable ordinal at which one considers the question. And in particular, it turns on whether the ordinal is minimal in a sense I'll make precise, or sufficiently non-minimal. So by minimal, I'm restricting to countable ordinals here. So we let alpha be a countable ordinal. And alpha is if and only if L alpha is pointwise definable. And I'll say that alpha is weakly minimal. If and only if there exists an alpha bar less than alpha, such that every element of L alpha is definable from this might be too thick a pen. Ordinals less than alpha bar. So that's at one end of the spectrum. And then at the, and there's grades of minimality. So one way to characterize the minimal ordinals is to say that the sigma 1 projectum of alpha plus 1 is omega. So the way I like to think about that is that the satisfaction of ZFC for a minimal ordinal is really quite fragile. It's true that L alpha, where alpha is minimal, satisfies ZFC, but if you consider classes that appear at the first possible level, then separation fails for omega, which is to say that the sigma 1 projectum of alpha plus 1 is omega. And the hierarchy that I have in mind here is as you increase the amount of satisfaction of separation and replacement as new sets appear before the next admissible ordinal, you're getting more and more robust satisfaction of ZFC. And one that's going to be of interest, it's a non-minimal ordinal. So alpha is bleak if and only if no new bounded subsets of alpha appear before the next admissible. And I'll write that as n alpha.
Peter, can I ask?
Yeah. Yeah.
I mean, do you actually have a thinner pen? Actually, it's rather hard to read, at least at this.
Okay.
End.
Yeah. Sorry about that.
I mean, the letters just merge into each other.
I can read it, but that's just because I created it, I think.
So that was
okay,
alpha
so
bleak, did you say?
Yeah, alpha is bleak, and the way I think of it is, it's like you're cruising up the constructible hierarchy, and then for a long time, no new subsets of L alpha appear. So it's it's a bleak landscape until you get to the next admissible. Right. Or equivalently, the L of n alpha satisfies that alpha is a cardinal. And another one that's going to come up is where L of n alpha satisfies that alpha is definably regular. Okay, so there's a spectrum here, and the behavior with regard to these with regard to these two questions is really sensitive to whether you're at one of these stages or one of these stages, and ultimately it's going to depend on whether you're at a bleak ordinal, whether you've got a very robust satisfaction of ZFC, or you're at any one of these other ones, non-bleak. Okay, so going back to the, so here's I'll first illustrate it with the phenomenon I'm talking about with forcing, and then I'll turn to categoricity. So a result of Stanley, which I think is really quite fascinating, is let alpha be a countable model of ZFC where alpha is weakly minimal. So there's some alpha bar such that everything in L alpha is definable from ordinals less than alpha bar. Then there's this real, NWG stands for non-weakly generic, with the following properties. It's not in L alpha. And when you add it, it's kind of like adding a generic set. You get a model of ZFC. And it's really out of reach of forcing. It's out of reach of forcing in this sense that it's not definably generic over L alpha. And it's not even definably generic over any outer model of L alpha that does not already contain it. So more precisely, if M is an outer model of L alpha and P is an M amenable partial ordering such that M with that class predicate satisfies ZFC, assume that the forcing relation restricted to sentences of bounded complexity is definable over that structure. Then if G is a maximal filter on P, meeting every dense subclass of P, which is definable over that structure, and you pick up the real, then you already had the real. Okay, and then at the other end of the spectrum, when we're dealing with levels where the satisfaction of ZFC is robust, so suppose that M is a countable transitive model and that M prime is a countable transitive outer model of M, such that the ordinals of M is definably regular, not just in hype of M, but hype of M and this outer model. Then there exists this partial order P in a filter G such that P is M amenable and definable over hype of M. And it's generic over M for P. And this outer model that you specified in the beginning can be captured as a generic. And in a way where the satisfaction of ZFC is pretty robust, you have that M of G with the predicate for the ground model M, P, and G satisfies ZFC. So there's a kind of like a dichotomy between the behavior of forcing with regard to this question of whether it's a universal method for capturing outer models that turns on whether the countable ordinal that you're taking to be your height of your model is minimal or very bleak in this sense that it's definably regular in height. So that's a kind of phenomenon that
Peter, could you clarify, is the forcing notion there, P, is that do you have ZFC in the language with that class P?
In the beginning, you mean?
In statement 2, well, the model where you have M, I mean, you're saying there is this partial order P, but I want to know to what, is it ZFC amenable to M?
I don't know.
And
Well, wait, yeah.
You're not assuming P is.
Yeah. I think it is. Doesn't that follow from the last statement?
Oh, well, that's about the forcing extension, but
You're throwing M in.
Probably it follows. Yeah. Okay. Thank you.
Yeah. So I find this phenomenon pretty remarkable, and this theorem is a generalization of a theorem of Max Stanley's. I was actually at Berkeley when Max Stanley presented that theorem, and in the question period, he said, you can actually do this. And it's, it uses a good deal of a combination of bar-wise compactness and class forcing. So now I want to turn to categoricity. And there's this remarkable theorem of Friedman from the early 70s. Suppose that phi is a sentence in the language of set theory, and that alpha is a countable ordinal, which is bleak, right? Such that no new bounded subsets of L alpha appear before the next admissible. So L of n alpha satisfies that alpha is a cardinal. So it's not as bleak as the ordinal in Wooden's theorem. It's just one step shy. Then the following are equivalent. ZFC plus phi is beta categorical at alpha, and ZFC plus phi proves in beta logic for models of level alpha that V equals L whole. So I'll just explain these notions. ZFC plus, I'm going to say that T is that better?
A bit faint now, but for me.
Oh, wait, what's happening here? Okay. T is beta categorical at alpha. Just means that there's at most one transitive model M of T. And when I say T proves in beta logic alpha phi, that means for all transitive M of height alpha, if that model satisfies T, then it satisfies P.
I guess in the first statement, you mean of height alpha, right?
Oh yeah, right.
And size beta or something?
Oh no, beta is just that we're restricting the beta models. So I could have put a T there, I guess, for transitive. So yeah, just that the beta just indicates that we're restricting to transitive models. Okay. So back to Friedman's theorem. Oh, so if you're at one of these bleak ordinals, then ZFC plus, it's really saying that the only categorical theory is V equals L. So if you have any phi, so if T is beta categorical at alpha, So suppose T is beta categorical at alpha and beta consistent.
You need to share your paper.
Oh, sorry. And beta consistent at alpha, then let M phi alpha equal the unique. So what Friedman's theorem is saying is it's saying that any sentence phi, which when you add to ZFC, which is beta categorical at one of these bleak alphas, the unique model is going to be L alpha.
So can I ask, is this anything to do with ZFC, or could we write down here ZFC minus?
Yeah, you can. He actually did it with KP.
Did it with KP, right?
And really the way the proof works is you assume that ZFC plus phi implies V doesn't equal L. And since that, so there's a set of ordinals that is not in it, and that is not in L. And then what you do is over the next admissible, you know that that set doesn't appear before the next admissible. Then over the next admissible, you can deal with the language for all of the sentence for sentences of length alpha, and then you can pin down a well-founded model using bar-wise compactness, and then you omit that set, and so you get a perfect set of models around if your sentence is implying B doesn't equal L. But this is completely open for minimal ordinals. So if you let alpha naught be the least alpha such that L alpha satisfies ZFC, then the theory V ZFC plus V equals L plus there does not exist a transitive model of ZFC uniquely picks out that model, right? And it would be really nice to show that this fails, so that by tying your theory to that model, you get something on the outside. Now, I should note that I've put a single sentence here. The way Friedman did it was he said he looked at recursively enumerable theories T. But if you do that, then there's a very quick answer to the question for the minimal ordinals even. And that's that ZFC is not the only RE theory, which is beta categorical at those minimal ordinals, because what you can do is you can take a forcing like Jensen's forcing for adding a pi12 singleton. And then you can write down, and suppose you got one of these minimal ordinals where everything's definable. Then you can write down a sort of nasty sequence of sentences, which uniquely characterizes the generic. And so what this collection of sentences is saying is it's saying, I am this particular generic extension via Jensen's coding. So, in the list of sentences, there's going to be a sentence that describes the L alpha least dense set. And if the sentence describes that, then you can start describing the generic by saying the first stem is the L least condition in this set. And they're all conditional sentences. And then on the outside, you can build the object. So it really does become trivialized if you look at RE theories. And that construction works for any of the strongly minimal ordinals. That's why I'm focusing on the single sentence. Looks hard to do with a single sentence. I'm just going to do it this way instead of sharing my screen. So Friedman also proved this other theorem. That first theorem concerns only oblique ordinals, but this theorem concerns arbitrary ordinals. So suppose that phi is a sentence in the language of set theory, and that alpha is a countable ordinal. Then ZFC plus phi is beta categorical. And suppose ZFC plus phi is beta categorical at alpha, then ZFC plus phi is going to beta imply for models of height alpha v equals Hod. And for this theorem, you don't need to use bar-wise compactness. You just use, I mean, you don't need to use what's called bar-wise's hardcore theorem. You just use the standard omitting types argument from classical logic. So if there were a phi such that some countable alpha, for some countable alpha, ZFC plus phi is beta categorical. So just suppose that, and then let's start deriving the consequences and see what it must look like. Suppose there's a beta categorical theory at alpha, and the unique beta model is not L alpha. Well, then we know that alpha has to be minimal in the sense that alpha is not a cardinal in height of L alpha, what I was calling L of N alpha before. And we also know that this unique model can't think zero sharp exists, because even if you have a fake zero sharp, suppose zero sharp exists in B, and then you use sigma 1, 2 absoluteness to get a countable transitive model in L that thinks zero sharp exists, the height of that model has to be bleak. So then you're in the regime of Friedman's theorem. And we know by Friedman's second theorem there that it's going to have to satisfy V equals Hod. Okay, so it's not L, right? Let's say L alpha, and it's not Hod. I mean, it is Hod, at the appropriate level. And it's not, it doesn't have zero sharp, even a fake one. Okay, now if you look in the, yeah, it's going to be a difficult thing to construct. So it's just, it's completely open, and if you have difficulty solving a light phase question, then the natural thing to do is to move to the boldface version. And that's what I'm going to do. So instead of looking at the L hierarchy, I just want to look at the L of X hierarchy under large cardinal assumptions. So we shift from L to L of X, and where X is real. So shift attention. X is real. And we're going to look at this on a Turing cone of X under strong assumptions. Okay, and what do I mean by strong assumptions? The background theory that I'm going to use is going to be, so a background assumption. For everything that I'm going to say, it suffices to have just delta 1, 2 determinacy, but this is a much more natural assumption. So there is an inner model with a wooden cardinal And for all sets X, X sharp exists. Now, for those of you who know intermodal theory, that's equivalent to M1 sharp exists and is fully iterable. Okay, so that's the background assumption. And under that background assumption, you get a lot of nice things. So we get, by Martin Steele, we get delta 1,2 determinacy. And we get sigma 1,2 determinacy. This implies sigma 1,2 determinacy by result of Martin. And you get that by Solovay and Kekris, you get for a cone of X, the Turing cone, L of X satisfies OD determinacy. And you get, since we've got sharps in the background by a result of Kekris and Wooden, that the theory of L of X for a cone of X is stable. So for the cone of X, so Kekris and Wooden, there is an X naught such that for all X Turing above X naught, the theory of L of X naught L of X equals the theory of L of X naught. Okay, so you're getting a lot of structure on a cone, and by a theorem of Wooden, we get that if you look at the Hod of this model, which is satisfying ordinal determinacy, for a cone, the Hod of L of X satisfies that omega 2 of L of X is a Wooden cardinal. And this is proved in the handbook article that Wooden and I wrote. So the main theorem, the first theorem, was that if you have determinacy in L of R, then the model Hod becomes really well behaved, and it ends up being a model that satisfies that theta is Wooden. And this carries over to models of determinacy in general. We knew before that under AD L of R had a lot of structure, right? You can pretty much settle any question that you ask about it under that background assumption. And we know that the model the model L is robust. It's the same wherever you compute it, if you're in a transitive context. And we know that the model Hod is very intimately tied with the background universe. So the behavior of Hod can radically change. Questions about it are sensitive to the background universe. But the remarkable thing is that when you look at Hod in the context of a determinacy model, it becomes very well structured. So this is the beginning of a whole series of results, which led to the conclusion that under AD, I'll just focus on L of R for a minute. The HOD of L of R is a fine structure model, but it's not one of the fine structure models in the old traditional sense. The Mitchell-Steele models are fine structural, but they don't have much information about how to iterate themselves. And the HODs end up becoming fine structural models in a new hierarchy, a hierarchy where there's large pieces of the iteration strategy in them. Okay, I'll say a little bit more about that in a bit. So we're in a boldface context, and for a real and an ordinal alpha, I'm going to let n sub x of alpha be the first x admissible ordinal above alpha. And I'm going to say that x is alpha is x minimal, if and only if it's not x bleak. So, which is to say that a bounded subset of alpha appears on the road from L alpha x to the next admissible. In other words, alpha is not a cardinal in the next admissible. So you're projecting. Before you get to the next admissible, you're projecting across alpha. And then this is the theorem. Assume that there's an inner model with a wooden cardinal, and that for every set x, x sharp exists. So we have all the things that I wrote down there. Then there's a sentence phi in the language of set theory, and we need two additional constants, c and d, such that for a Turing cone of x, if you interpret c by x, then for all countable ordinals, if you're at a level that satisfies CFC, whether it's bleak or not, then there's an interpretation of D by an ordinal less than alpha, such that there is a beta model of ZFC plus phi of height alpha, and it's not equal to L alpha of x. Okay, so the open question that we were looking at before was trying to get around Friedman's theorem at the level of minimal ordinals by getting beta categorical theories, which where their minimal model was not L alpha. Now everything's relative to a real. So we're looking at beta models which are not equal to L alpha of x. And in addition, if that ordinal alpha is x minimal, so you're not in the Friedman regime, right? Then there's a unique beta model of height alpha, and it's off to the side of L alpha of x. So this is best possible because by the Friedman result, if you generalize it to L alpha of x, if you're at one of these bleak points, then you can do a similar barwise construction and get a perfect set of objects if they're implying that you're not L alpha of x. But when you're at one of the non-bleak ones, one of the minimal ones, things are so tied to that model that you can canonically describe this object outside. And the sentence just fixes that. And this, this object has some nice canonicity properties, which I'll discuss. So what I'd like to do is describe a little bit how this goes. And I'm going to focus on the simple case. I'm going to focus on the minimal alpha such that L alpha of x satisfies CFC. And x is going to be a sufficiently rich real. And I'll tell you just how rich it has to be. And then I'll give a brief outline of the way the proof goes. But this is probably a good time to stop and ask if there's any questions about what I've said so far. Okay, as you probably know, wooden cardinals are really a mixed blessing or more like a mixed curse, because they started off as throwing a wrench into the intermodal theoretic machinery by all the intermodals that were being built had a projective well-ordering of the reals, but then the result of Shalon and Wooden showing that if you have sufficiently many Wooden cardinals, then all projective sets are Lebesgue measurable, showed that that machinery is going to have to change. And what had to change was the use of just linear iterations to compare. So the Wooden cardinals forced us into a situation where you had to start considering iteration trees, and then it became an issue of picking the branches through those trees. But it's an interesting wrench that was thrown into the machinery, because it happens to be that when you're in the machinery and you have this wrench, if you apply some ingenuity, you can actually use the wrench to fix the problems that it created. So the way you end up picking these branches is by looking for these things called Q structures, which is where you see the failure of the woodenness of the common part model. So I want to describe just a bit of the machinery that goes into this, and it's based on the Hod analysis, not of L of X, that's still open, but of L of X and G. So what I'm going to do is focus on, the alpha least such that L alpha of X satisfies ZFC. Okay, and how high is X? Up the Turing reduction order is X. Well, under our background assumption, we get an intermodal for a Wooden with a countable ordinal, and there's a canonical one, and it's called M1. So it's the canonical intermodal for a Wooden cardinal. And I'll write delta of M1 for the Wooden cardinal, and delta of N1 of M1 is countable. And M1 has the form L of M1 cut to delta of M1. Okay, so it's got this extender sequence up to delta, witnessing that delta is a Wooden cardinal, and then after that it's just L. So this is a countable object, and M1 is uniquely constructed from it. So we let X be Turing above. I'm going to call this here M. Turing above that. Okay, and then when you do that, now we're in L alpha of X, alpha minimal, such that L alpha of X satisfies ZFC. Okay, so now we're in this context of L alpha of X, and we've got a canonical model for a Wooden cardinal. Now, we want to use that model, but we don't want to refer to it de re. So, because we want everything to be definable. What we're trying to do is we're trying to give an analysis. we're trying to get a canonical model in this context. It's going to be ordinal definable. And then the branch, and then the object that we're going to add to it is a branch that is unique. And it's not in L alpha of X, but we can describe it using machinery in L alpha of X. So backing up just a bit. For X, a real, let kappa of X equal the least inaccessible in L of X. And we have that just because we've got sharps. And let G be a generic sorry. For the Levy class, then for a cone of X, we do this. Then there's a Hahn analysis for L of X and G on a cone. And what you get is that you get that on a cone of X, if you're in one of these contexts, and it's for technical reasons that we had to take the symmetric collapse, you want all your models to be countable. And Farmer Schletzenberg showed that that comparisons can lead to models of height omega 1 of L of X. And so you need to keep everything in the countable regime. So you use that symmetric collapse. So there's a Hahn analysis for that. And it shows that for a cone of X, Hahn of L of X G is a fine structure model. But the interesting thing is, it's not a regular fine structure model. It has the form of L of model M infinity, which is going to be an iterate of an M1. And it's got some additional information. So if I just put a square bracket here, that would be a regular Mitchell-Steele type model. But it has this fragment of an iteration strategy. So outside in V, we have M1 sharp and we have M1. And we let sigma 0 be its iteration strategy. Then you can take that iteration strategy and add it where you restrict to this collection of trees. And those trees are the ones that appear before the first inaccessible above M infinity. So you're realizing Hahn, which on the face of it could look really complicated, but it turns out to be well behaved in the context of a determinacy model. You're analyzing it in terms of a fine structure model that has a good deal of information about how to iterate itself. Okay, now, this is one of the most beautiful proofs that I've seen in both directions. You want to get all of this material from a fine structure model that you're targeting in an ordinal definable way in L of X and G. And that means you can't refer to anything, directly. You can't say, okay, I'm going to take M1 and I'm going to iterate it. But what you can do is you can say something that covers a bunch of cases, and which is such that M1 is included in those cases. And then you talk about all that, and that allows you to indirectly do things with M1 without specifically referring to it. And so this motivates the notion of an M1-like model. And an M1-like model is this. So definition. The primos N is M1-like if there exists a delta, and I'll call it delta of N, such that N equals L of N cut to delta of N. Okay, so that's something that M1 looks like, right? It's just L above its delta. And then you write down a bunch of other first order properties of M1. You can write down as many as you want. So one is N satisfies that delta of N is wooden. And two, for all eta less than delta, and oh, well, I gotta do this. If you take L and instead of throwing in N cut to delta, you cut it further to eta, then that does not satisfy. Eta is wooden. So this is the minimality, right? And then the third is that N satisfies a certain amount of iterability. So for all eta less than delta, it thinks I am eta comma eta iterable. Okay, so those are all properties of M1. And now working in L alpha of X or L of X and G, we can just say, consider all of the M1-like models that are countable, and then we can do things like simultaneously compare them. And when we do, we're going to get a model. L alpha of X is going to be able to track the iteration strategy that's outside in V for a while. And we're going to get a model which has a wooden and which is M1-like and has the feature that now it's definable, it's ordinal definable. So I'm just illustrating something that goes into this. You want to be able to start accessing things in an ordinal definable way without referring to any particular one. So you take the thing that you want to talk about, you write down some first order properties of it, you consider all the things with those first order properties, and then you run this big comparison process. And in the end, you're going to get a common iterate. And it's going to be a common iterate that is also an iterate of the M1, the thing that you wanted to talk about but couldn't talk about directly. Okay.
And is this the M infinity?
Pardon? Yeah, that's
M infinity is the direct limit of this.
Well, it's not really this. It's what we use in our proof. The directed system that goes into getting this is more complicated. But I'm just trying to illustrate how you can, in a very sort of simple way, how you can get an ordinal definable M1-like model by doing a big simultaneous comparison like this.
Right. Okay,
so these are features of M1. And remember, I said earlier that wooden cardinals are a mixed blessing. One way in which they're problematic is that they show that these models can't know too much of their iteration strategy, these M1-like models. And the reason has to do with the genericity iterations. So if you have an M1-like model, which is iterable, and then there's two sort of genericity theorems that would improve. The first one, and they're both remarkable. The first one is that if you take any real, there's a way of iterating your M1-like model so that that real is generic over the iterate. And it's similar to a comparison process. It uses this thing called the extender algebra. And so you have this extender algebra, and it's got these infinitary sentences, and you're trying to satisfy a certain theory, which will uniquely determine this real X. And anytime a sentence doesn't satisfy it, you hit the extender corresponding to that sentence, and then that just gets rid of that problem. And you can show that it converges. And then in the end, you've gotten rid of all the problems. And so you've got a model that satisfies the target theory. And that shows that X is generic over it. Now, you know, it's similar to what happens with ultra powers. If you have a model with an ultra filter and you take the ultra power, then the ultra power can't see the ultra filter. It can't have that kind of awareness, because if it did, then it would be able to collapse the image of the critical point. And what happens with these genericity iterations is very similar. So you end up iterating to make something generic over the iterate, and the model can't see the branch, because if it did, then just as in the case of the ultra filter, it would see something it can't see. It would collapse a certain cardinal. So, you know, let's say you're in L of X, and you have this M1-like model. Now I'm going to refer to it de re. I could, inside L of X, iterate M1 so that X is generic over an iterate. So we've got M1 and we've got its delta. And, you know, that's a countable ordinal. So you get this iteration tree, T, and you get a final model. Oh, so this is M1. And then you get this final model. I'll just write M infinity, such that, and you know, we'll call the extender algebra here B of delta for omega, and then you know we get this on the outside in B. There's a map. This is delta infinity, such that this map on the outside, which we can't see inside L of X, I'll show you that in a minute, is going to be the extender algebra of this model. Okay, such that X is generic over this. Now, this extender algebra is delta infinity CC. And what we're doing is we're adding X over this. So M infinity with X added is really just L alpha of X. So you're in L alpha of X. Oh, I wasn't using alpha here. You're in L alpha of X, and you take this model, it doesn't have X in it, and then you iterate it to get it a model which is such that X is generic over that, so such that you are generic over that final model. And what you end up showing is you end up showing that L of X can't see this branch. So there is a branch, but the branch is not in L of X. And the reason is that since this is delta infinity CC, this has to be a cardinal. I mean, this is a cardinal, but the iteration, you show that, and it has to be a cardinal in L alpha of X, a regular cardinal in alpha of X. So delta infinity is a regular cardinal in L of X. But if L of X could see the branch, then it would see that this co-finalizes that regular cardinal, and that's a contradiction. So what you end up doing is you're working in L of X, and you can iterate these objects for a long time. But because of these genericity iterations, for reasons similar to what happens in the case of an ultrapower, you can't see the branches, but you can see the final model. Okay, and that shows that, you know, these M1-like models, although they are eta iterable for all eta less than delta. I mean, that's one of their defining characteristics, right? They think I'm this iterable. They can't be delta plus one iterable. They can't see these branches, because if they could, they would be collapsing things that are cardinals. And the remarkable thing is that you can add the branch back to this model without adding any new bounded subsets and without killing the wooden cardinal. So you get, you have M1, and you can add the branch back in. And the result is that M1 up to V of its delta equals M1 of this branch up to V of its delta. So you're not adding any new bounded subsets, but you're collapsing. This collapses delta plus in the sense of M1. And it's actually doing, you know, devastating damage to the cardinal structure of M1. It's really just a subset of delta, but it has the feature that it preserves a wooden. So you get that when you add this, M1 of B still satisfies that delta is wooden. And that's what's, you know, fascinating. You're adding a set to delta, which is doing devastating damage above by collapsing all these cardinals, but it's not injuring the woodenness of that ordinal. And so the way this proof goes is you're working in L alpha of X, you do a big simultaneous comparison and genericity iteration to get a definable model. And then you do a subsequent construction called a quasi-limit construction of self-genericity iterations. And it turns out that you can see in L of X the branch for that final model. And the fact that you can see the branch for that final model allows you to show that there's a unique branch that you can't see over the first iterate of that big simultaneous comparison and infinity. And what the sentence says is it says, I am n infinity, which is a result of doing this big definable thing with this branch through this particular tree. And that's what this ends up being. You get that it's L alpha of X of B, and that construction is uniform across all the ordinals. Okay, so I think I'll end there.
All right, thanks very much, Peter. That was fascinating. Any questions or comments from people?
I have a question. So I was wondering if you could give us some kind of high-level explanation for understanding why there's this bifurcation between the pointwise definable case and the non-pointwise definable case. I mean, in the remarks, in the theorems of Friedman and so on that you were mentioning at the beginning. And why should we expect those cases to be so important for the existence of beta categorical sentences?
You know, I think I can get a grip on it in this case. In the light case, I can see what's going on when you deal with recursive theories. But it's open with regard to single sentences phi. So I guess I'll say two things about this. The first is that, so we've got this boldface result, right? Holding on a cone. And there's no known, it'd be surprising if the light face result was provably false, right? Because usually if you have a light face result, you can relativize it to a real. And so it's interesting either way. If it's
which way, when you say provably false, which way? I'm sorry.
Oh, provably, if you can't have the analog of this for the light face case.
Okay. So if
this is evidence
result for pointwise definable models, in other words, it would be surprising to prove it in the pointwise definable case. Is that what you're saying?
Sorry, I couldn't hear you.
So you're saying it would be surprising if the Friedman result went through for the pointwise definable case? Or are you saying the opposite of that?
Yeah.
Okay.
If the Friedman result went through for the pointwise definable case, you would expect that proof to generalize to the boldface case.
Okay.
But this shows that it can't. And there's no known result that holds on a cone but doesn't hold in the light face case. So if Friedman's result is provable more generally, then this is an instance of a new kind of phenomenon because you have something holding boldface on a cone but not light face. And if Friedman's result isn't provable, but this can be brought down, then that would be, that would be fascinating because
Okay.
yeah. So that's the first thing I wanted to say about this. And the second thing I wanted to say is, in answer to your main question, it's really bar-wise compactness combined with omitting types that is doing all the work. In the case where you've got bleakness or sufficient non-minimality. Right. It's a big, like Max Stanley says in his paper, Outer Models and Genericity, he said, it's a really nice quote. He said something like, in some sense, proofs like this are bound to be,
you're doing bar-wise compactness over the next admissible above the model, and the point is that if there's some set that's not in L, then you can omit the type that set would.
Yeah.
And that's how the proof is going. I see.
Yeah, and then it's a much more complicated argument in the wooden Stanley type theorems, but that bar-wise compactness over the next admissible, where it's definably regular, gives you enough machinery. The compactness gives you enough machinery to construct outright these, any outer model.
Right. So normally I think about pointwise definable models as ones whose theories are extremely non-amenable to the model. The model just can't ever know its theory in any way, because then that would be, the theory determines the model in the pointwise definable model. Whereas these other ones, okay, maybe the theory is somehow a little bit amenable. And so I was hoping for an answer that would involve that kind of intuition, but you didn't say anything like that. So I'm not sure if that's right. Maybe it's just the wrong way of thinking about it.
Another way to get it so going back to the Friedman context, if you deal with RE theories and not just specific sentences, then what's doing it for you at the minimal ordinals? The way you're able to get things out that are not equal to L, but still have a theory which is beta-categoricity, beta-categorical, is by using the fact that everything's definable in your model to write down a description of the generic off to the side, right?
It's sort of like Simpson's proof that for every countable model, you can augment it with a proper class predicate, which becomes pointwise definable. I mean, this is what Reitz and Lenitsky and I used to show the pointwise definability theorem. I mean, that every countable model of set theory has a forcing extension, which is pointwise definable. We do something similar to that because we sort of, I mean, the Simpson trick, right, is you enumerate the dense classes and then you extend the generic filter by a minimal possible amount that accords, that meets that dense set. And it's very similar to the way that you're describing that argument.
Okay, I should look at that.
Well, thank you very much.
So perhaps I might ask, I mean, in the earlier part of the talk where you're talking about Max Stanley's results, this was somewhat reminiscent of an argument that I think the Woodin told me once over tea or something. It went by very quickly and I can't recall it exactly, but there was something about taking countable models and defining some class generic forcing over that model, and such that there was actually just one unique generic for that model.
That is funny because that's the way I got interested in this. Hugh remembered this result of Max Stanley's, of the form that you just mentioned, and he misremembered because if you look at Max Stanley's paper, that's not what he proves.
I see, right.
That's self-encoding forcing, though. You can definitely do that, Philip. This is used in the geology results. So you can do any forcing at all, and then you code that forcing into the GCH pattern, say, and then you added new stuff, so you code that in, and then code that in, and so on. If you just iterate that, then there's going to be a unique generic in the extension.
But so are you getting the beta-categorical theory, or
no, because there's a lot of different generics, but inside any one of them, there's only one generic filter for that forcing.
No, this was different. This was saying there's just one generic.
Just one.
Oh, I misunderstood. I see.
Yeah. And then we looked at the paper. And, I mean, he would always quote this and say, "Isn't that amazing? This is like the most workable."
Yes.
And then it's not proved yet. So that's the reason we went down this road. I mean, that would be the beta-categorical case of the light-face, Friedman theorem.
Right. Okay.
I mean, if you had definable forcing relations, there couldn't be any such forcing because you could define the generic in the ground model. I mean, right? How can there be a forcing notion that has only one possible generic? I mean, if you have incompatible relations, then there can be different generics. I mean,
we're not even asking for a forcing. We're asking just for an object which can be, uniquely described, like in this case. So, I mean, another way to put it is, this looks like something that would be very hard to do with forcing.
Right, I see. Well, so you want just an implicitly definable class that's amenable.
Yeah, these branches are strange objects. They're, it's not the branch is not living in here. There is a branch living in here, and that the branch that's living in here allows you to describe implicitly the branch that's not living in here. And you can say that I am L of alpha and X and that. And the minimality, the first part is describing, what level you are. The base case, the base model, and that's where the minimality is being used. If you take an arbitrary, if you're dealing with minimal ordinals, they're not problematic to describe. But the thing is, this is living over any. This branch is living over any alpha, and it's uniform. That satisfies ZFC, and it's uniformly describable, so long as alpha gets collapsed before the next admissible. So the case where you're dealing with the minimal levels is not so bad. But the more general version looks hard. And this object is a pi1 singleton. And if you collapse, it's a pi1 2 singleton. And if you're looking at L alpha of X and you start going through outer models, as soon as you get to an outer model, that thinks the sentence, then it's correct about the branch B. And then, that doesn't get injured as you go through larger outer models. So it's reminiscent of that real X and WG that Max Stanley came up with. Because remember, that was not, if you took any outer model of his L alpha and you looked at a definable generic extension, if that definable generic extension picked up that real, then it was already in the outer model that you started with. This is more general, because if you take any outer model and an outer model of it picks up B, I'm not saying a definable generic extension of it picks up B, then you already had B. I'm saying that if an outer model, any outer model picks up B, then you already had it, and that's by the absoluteness of this object. So in some of Stanley's terminology, it's not even invisibly generic over an outer model. So it's further out of reach than that XNWG.
I have another question, if I may, but if anyone else has a question, please go ahead, because I've already asked several. So my question is about this uniformity of alpha, because this theorem that you have up there now is about sort of all alpha at once, but I think the Friedman theorem was just about one alpha at a time, right? And so how is there any kind of robust Levenheim's golem phenomenon for beta logic that talks about sort of having different alphas, or how important is it that you're getting this thing for all alpha, or as opposed to just one at a time with a separate formula or something?
Yeah, so his result shows that for each one. Ideally, what you would like is an analog of V equals L, right? In the sense that it's just the one sentence and it's uniform. If you're looking for something that's very similar to V equals L, then you want it to hold, assuming there's a proper class of Worldly cardinals, you want it to hold all the way up. The Friedman result really does require restricting to countable ordinals, because if you look at uncountable ordinals, then it doesn't hold, right? Because zero sharp, like any uncountable transitive model that has 0 sharp is going to be correct about it. So you want to stay within the countable regime, because there you've got absoluteness. So the statement that a theory is beta categorical for the countable regime is a pi 1-2 statement. So yeah, I think really one would like an analog of V equals L for as much as for as far as you can go. I mean, this is just doing it in the boldface case. It's an analog of V equals L of X, where, you have this constant to describe X. And I should say, in constructing this, we need to get everything ordinal definable, so you can't even refer to X. So what you do is you wash that out. So you make every real, just think the same thing you did with M1, right? You can't refer to M1, so you refer to all the things that are M1-like. So you can't refer to X, so you refer to all the things that are X-like. Well, what's that mean? Well, it's a real, you can refer to the reals, and it's such that it constructs the universe. And then so, you can do things like make all of those generic over the iterate.
I have another question, but I don't want to take up the whole question period.
Anybody else want to have a go?
I have a question, but Joe, you can go ahead first. It's fine.
Okay, so I mean, sort of on a more philosophical point, I mean, throughout most of mathematics, categoricity results are thought to be extremely important in identifying the most central fundamental structures like the real numbers or the Dedekind arithmetic and so on. They satisfy categorical theories, and that's held to be extremely important. But in set theory, the categorical theories tend to be these minimal theories, which are not thought to be the most important set theoretic theories like V equal L and so on. And so I was wondering, I mean, and it's related to this move to countable structures, because you can't have categoricity, the categoricity results fail about the V equal L case, right? For uncountable cardinals.
The uniqueness results fail.
Right.
The result that V equals L is the only one fails.
Right. I see. So, I mean, like Robin Solberg and I are looking at this kind of tension between categoricity and reflection, right? This a kind of, in set theory, be like reflection, which is an anti-categorical property, because it's specifically saying that if something's true somewhere in the whole universe, then it's also true along the way. That's an anti-categorical result. It doesn't quite fit into your beta categoricity framework, though, because the height is changing, right?
Yeah.
So what are your feelings about that? I mean, how should we think about categoricity? Do we like it or do we not like it? Or when the fact that V equal L is the only categorical one down low, does that make us like V equal L or not like it? Or what is the reaction that we should have to that result?
Well, since it includes the word like, I guess I'd have to speak from a first personal point of view, I don't know what philosophical significance it has. I mean, it is interesting that you just ZFC plus V equals L plus it does not exist a transitive model of ZFC, just picks that object, uniquely. And I think just even asking about the minimal ordinal, is there anything off to the side which with one sentence you can pick, right? If you allow yourself an infinite number of sentences, RE, then you can, do this kind of threading argument, describe that generic, but that's kind of cheating, Is there just one sentence which does it? I just find that a fascinating question. Could be that there's, a perfect set of canonical objects around L alpha naught. I mean, categoricity is great because you know exactly what you're talking about. But the question here is really, are there any other things at that height that where we can know exactly what we're talking about in the sense of categoricity?
But I mean, in a sense, we don't expect V to satisfy that kind of categorical theory, right? Isn't this the usual view, the usual large cardinal view, or the strongly reflection view, is that you don't expect the full set theoretic universe to be in any sense categorical. And so the fact that
you mean, but you mean the theory of it, or it means to talk about an object being categorical?
I mean that it satisfies categorical theory, or a sentence or whatever.
I should take back what I said just a minute ago about there being a perfect set. I mean, if we're just doing this one sentence, you can't do that. But if you have these lists.
So thank you very much. Farmer, go ahead.
Oh, yeah.
Yeah, so I'm just wondering whether you've ruled out any other like natural candidates for producing a beta categorical theory, as in you mentioned that you can't have zero sharp in a unique, or the model can't think it has zero sharp. Therefore, it would have been a natural candidate that phi is the sentence V equals L of zero sharp.
Yeah.
So that one's ruled out, and likewise, V is some particular set generic extension of L. It's also doesn't work. Are there any other natural candidates that you've ruled out for producing a beta categorical theory?
You mean in the light phase case?
Yeah, light phase case.
Yeah. No, those are pretty much the main ones that I know. It's got to satisfy V equals Hod, and it can't have zero sharp.
Yeah, V equals Hod as well. Yeah.
Anything that I guess one thing one could do is start looking at all the things that force the height of the model to be bleak. Get more statements like it can't have zero sharp, and kind of like zoom in on it. But yeah, it's weird. It can't have this sharp, but it's analogous. I don't know. Maybe this is a loose analogy, but there's that master tree, such that when you add the branch through it, it adds the sharp. And then it adds then that sharp adds the branches through all the tree.
All of them. Yeah.
Yeah. And that master tree is kind of like, maybe it's a loose analogy, that's kind of like in the light phase case, it not being able to have zero sharp.
Yeah.
It has to satisfy V equals Hod. And it can't have zero sharp, upstairs, that's like saying it has to satisfy V equals Hod, and it can't have the master tree, because the master tree would give you a fine structural model that had not just the iteration strategy up to the next inaccessible, but like the whole thing. So maybe there's a way of just looking at this tree and seeing downstairs whether there's anything analogous to that.
That's very interesting.
Thanks.
Any more questions or comments? And I get a sense that we could perhaps wind up the formal part of the talk, but of course people can stay if they wish.
I have one more question.
Oh yes, go ahead.
Isn't this bleak terminology unnecessarily pejorative? I mean, because like your favorite large cardinals, inaccessible cardinals, and so on, they're all bleak, right? I mean, but that doesn't.
Yeah, but the thing is, I love desert landscapes so much.
I see. Okay.
That for me it's an honorific.
It's sort
I'm
of
thinking
harsh.
tundra rather than desert, but
Like, you know, the loneliest road in the world that goes through Nevada. That's what I think of when you get
I see.
great road.
oh, hot and bleak, right? I was thinking cold and bleak. Okay, right. Well, thanks very much, Peter. That was
Okay, thanks for having me.
applause,
Thanks.
audible and inaudible to you. Thanks very much.
Thanks, Peter.
Yeah, it was very interesting.